Hello, welcome to the second part of NP-Completeness and Reduction. And one more time, I'm gonna repeat what we're doing. I'm just gonna keep on hammering this point until you're bored of it. What are we trying to do? We got problems in NP, we got problems in NP, and you want to know if this NP set is special or not, or if NP just P, right? All these problems in that can be verified in polynomial time, but we can't do them in polynomial time. Are they just something that you can do in polynomial time anyway? Right? Basically, are all these problems special or not? And we also mentioned a plan to do this. Well, we're gonna go through every single one of these problems in NP, and then show that every single one of them is in P. Well, that's the plan. Or the second option is to show that if there's at least one problem here that you cannot do in polynomial time, you have to be able to prove that you cannot do it in polynomial time, and that is pretty hard. If just one problem cannot be done in polynomial time, then this NP set is a legit new class. So it does actually exist, because I can't put this dot inside P, right? Just one problem with that property, and you're also kind of done. But of course, what we want to do is we want to make things easier. We don't like seeing things stay hard. So the goal is to show that every single problem is in P, which I don't think is possible. That's just a personal opinion. And guess what we're gonna do? We're going to introduce yet another complexity class. This one's gonna be called NP hard. Well, you can kind of ignore sub exp from now on, but we still have four. We have exp, we have np, we got p, and I'm going to draw NP hard here later on. So what is this guy NP hard? Informally, NP hard is a class of problems that are as hard as any problem in NP. You're gonna see that definition in Wikipedia and most textbooks. They're gonna say that. It doesn't mean much. At least to me, when I read that, I thought, well, okay, what does that mean? So we gotta talk about something else now. We gotta talk about reduction in order to see why we have NP hard. Earlier, I talked about decision problem versus optimization problem, and hopefully by now you have a good feel on which one is harder. If I have the algorithm for the decision problem, then I can get the answer to the optimization problem. You saw what I did, right? Just do a bit of modification, just keep on asking the same question. And if I have the solution to the optimization problem, I can just get the answer to the decision problem. So doing one helped me with the other one. But look, these are actually different problems. Even though they have the same setting, you are still answering a different question. It's a different algorithm just because the answer is different. And the thing is, you can actually convert from one problem into another problem, even if they're completely different problems. Well, I guess they have some similarity because you can convert from one to the other. But what I mean is this: you know, all these little dots. Let's say they are different problems. Let's say this is traffic salesman. Let's say this is I don't know, FedEx cover, minimum FedEx cover, and this is knapsack. So they worked out that these problems in NP, they can actually convert from one problem into another problem. So if I convert this one into that one, I can use the solution of this one to solve that one as well. Well, actually, you can also convert maybe from, let's say, from this dot here, you can also convert it into exp here, like sorry, for a problem in exp. But yeah, maybe that won't be so interesting. So why do that? Anyway, why do you want to convert? What do you want to convert from one problem into another problem? Well, I thought before we talk about that, let me give you an example first, so you understand what I mean by converting. Remember, we're not converting from decision problem to optimization problem anymore, or vice versa. We're converting from one problem into another problem. And the example that I'm going to use is I'm going to convert a Hamiltonian cycle problem into a traffic salesman. So Hamiltonian cycle, we talked about that in the previous lecture. It's a cycle from one vertex back to itself that visits every other vertices once. And traveling salesman, hopefully you've heard about it. It's a route from vertex A back to itself if you visit every other vertices once. And because this is a decision problem, not optimization, we can ask that if is the cost m or less. We're gonna have something like that. So even by looking at the problem description, you might be thinking they're kind of similar, right? Well, because they're both based on graphs, they both have a starting point, they both require you to go back to the starting point after you visit every single node in the graph. I guess the difference is with Hamiltonian cycle, I don't care about the weights. I just care about the path. In traveling salesman, you do. And also, the one thing you have to watch out for is that in traveling salesman, you're actually given the distance between any pair of cities. So what I did was, from the Hamiltonian problem, I created an instance of the traveling salesman problem, and I give the edges a weight of 1, if there's an edge in the original graph. And all these edges that I added, the yellow ones, I gave it a weight of 2. So there's actually more edges here. I just don't want to make it too cluttered. Anyway, all the yellow ones, all the new ones have weight 2. Now I'm going to solve this traveling salesman problem. And I'm going to ask, is there a route that costs V or less? Where V is the number of nodes in the graph. Why V? Well, because if I visit every vertex, and then I'll go back to the original one, that will cause, there will be 3 edges in that cycle, right? And if I use only the edges in the original graph, the weight of that path is going to be exactly V. Because you can see that in the graph for traveling salesman, all the edges in the original graph cost 1. So if I can't find a solution in the traveling salesman problem with weight V, that means the route uses one of the yellow edges, which is not in the Hamiltonian version. So that means there is no Hamiltonian cycle. So the traveling salesman couldn't find such a cycle. Okay, you see how that works? You see how I use the traveling salesman solver to solve a Hamiltonian cycle problem. The conversion that we just did is what we call a reduction. And this is something that we want to be able to do in problem in time, but we're going to talk about that later when we discuss reduction in greater depth. Right now, I'm just giving you an overview of what reduction is. And the most important point is for you to understand why we want to do reduction. I'm not going to call it conversion anymore, just so you get used to the word reduction, because we're going to be using that from now on. And the idea is, I want to solve A, but I don't know how to solve A. I know how to solve B. So what I'm going to do is I'm going to convert A to B. I'll solve B, I get the solution, and I convert it back to A. And the thing is, you have done a lot of reduction, even back in Comp 1 to 5. So what do I mean? When did you do it? Well, let's say I give you this problem here. You're in LinkedIn, and let's say you're this guy in orange here, and these are all your connections. And you're wondering if everyone in the Macquarie University network is either your connection or a connection of your connection. So 2 hops away. So I imagine if I give you this problem back when you're in high school, you probably can solve it. But in Comp 2 to 5, you learn about graphs, you learn about BFS, and well, now when you see that problem, you think, right, I'm just going to make a graph. I'm going to put people in those nodes. Then I'm just going to do a BFS, breakfast search, starting from me, and I will only go 2 deep. Okay, so maybe you can say that this is just an abstraction, fair enough. But you are converting a real life problem into a graph theory problem. And the funny thing is, it's probably obvious to you now that this is what you have to do, but how do you solve this before you knew what a graph is? Because I had no idea. I'm sure I can solve this back in high school before I learned what a graph is, but I would have a different way of thinking. And that means this graph theory problem, well, actually this problem here, this LinkedIn problem, it's a different problem. It's just that I can apply it. I can apply a graph theory problem to solve the LinkedIn problem. You see how I'm reducing a real world problem into a graph theory problem. Well, it's a very loose way of saying what reduction is, but yeah, it kind of works. Maybe a better example is the arbitrage problem that we talked about in the workshop. Well, I'm not going to talk about this problem here, so you can check out the workshop recordings if you don't know what this is. This is probably the best example I can think of, because you went from a problem that doesn't seem to have anything to do with shortest path, and then we convert that into an all-pair shortest path. And we can use Floyd Warshall, we can use matrix multiplication to work out if you can make money from buying and selling currency. Again, if I just give you this problem, even like just a few weeks ago, if I just give you this problem, I don't know how many of you can see that as a shortest path problem, right? So this is a very cool example of reduction. And another example of reduction, and this is true story. This is a true story. A student in Com 125 didn't know how to code linear search. Actually, I should not say linear search. It's actually find the largest element, which was done using a linear search back in Com 125. So sorry about that. So he didn't know how to find the largest element, but he knows how to use collections.sort because he's used Java before. So can you guess what the student did? Yeah. He called collection.sort on the array list and then returned the last element in the array list. So I wouldn't say that student is great in coding, but he's pretty creative in the problem solving department, right? So my point here is that you know what a reduction is, you have done it, you have been doing it, the concept is nothing new, and the main reason why you did reduction is to solve problems using the tools that you have. You're kind of doing this conversion in your head when you solve problems. Now, in this unit, we're not going to use reduction to solve problems. We're not going to use it to solve NP problems, because solving NP problems are hard. We're going to be using reduction to argue about the difficulty of a problem. And what do I mean by that? Well, think about searching and sorting. Which one is harder? Sorting is harder, right? So, if I can use sorting to do searching, well, to do find maximum, which one is the harder problem? Find maximum or sorting? Can I use the find maximum algorithm to do sorting? Well, no, I have to do extra stuff. But you kind of see which one is harder and which one is easier. Just keep this at the back of your mind. And now let's go back to NP-hard. All right. So earlier we said that NP-hard is a class of problems which are at least as hard as any problems in NP. That is still not really making much sense right now. So let me give you a formal definition of NP-hard. Problem H is NP-hard if every problem L in NP can be reduced in polynomial time to H. So in other words, we can convert any problem in NP to any problem in NP-hard. So that means you can use the solution for H to solve every problem in NP. So if you have this problem H here. So what do you think is harder? A problem that is NP or a problem that is NP-hard? Like, think about the sorting searching which I just said in the previous slide. So does it make more sense now than when they say NP-hard problems are as hard as any problem in NP? Because you can use NP-hard algorithm to solve any problem in NP. So these are special kind of problems. We had NP problems, and now we got NP-hard problems. And anything in NP can be reduced down to any problem in NP-hard. So any problem in NP-hard, if I have the solution for any problem in NP-hard, I can use that solution, I can use that algorithm to solve any problems in NP. And that is going to be a very important fact. But before we talk about why, just think about NP hard and think about NP. Do you think that NP hard problems are also NP? No. We only said that you can reduce a problem in NP into a problem in NP hard. So problems in NP you can verify in polynomial time. I never said anything about verifying problems in NP hard. So these problems in NP hard, you may not be able to verify them in polynomial time. May not be able to. So some problems in NP hard you can. So that means that some problems, so this is what we have. We have NP, this is what we had before. And now I got this set NP hard. So some problems I can't verify in polynomial time. Some problems I can. So that's the intersection here between NP and NP hard. So what happens if P is equal to NP? Does it look like this? No, this is not what's going to look like. So for now, just stay with this, just stick with this P and an NP in different sets for now, right? We're going to see later what happens if P is equal to NP. In particular, there is yet another set that you have to worry about, and that is the intersection between NP hard and NP. So let's count. You got EXP, NP hard, NP, P, and one more guy, and you can guess who this guy is. NP complete. Now, if a problem is an NP and also in NP hard, then we call that problem NP complete. So the class NP complete is a set of problems which are both NP and NP hard. That is, every problem in NP can be reduced down to a problem in NP complete, and every problem in NP complete can be verified in polynomial time because it is an NP. So it's like saying NP complete is stronger condition than NP hard. Well, I probably should note that in the exam, I refer to some problems as NP hard, but just saying something's NP hard, they may be NP complete as well. So yeah, just saying if in exam if you see NP hard, they can be NP complete. I just say, well, you don't have to worry about them being NP complete. You don't have to worry about them being that you can verify the solution in polynomial time. And also, NP complete problems, we're gonna say they're always decision problems. So are NP problems actually. We're just gonna retcon that because I didn't really say that they are decision problems in the previous lecture. Okay. So that is the definition of NP complete. This guy here, that intersection. So yeah, you have a picture of a happy family here. NP hard, NP complete, NP, NP. So make sure you understand the definitions. Make sure you're okay with all the definitions that we have done so far. Now, which one do you think is more important, NP hard or NP complete? Well, let's talk about why NP hard is not that important. Well, at least in comparison to NP complete. So, what is it that we want to do? Our focus is on the set NP, right? We only care about problems that can be verified in polynomial time. And when you look at this picture, these guys inside NP hard, can you verify them in polynomial time? No, you can't. But these guys NP complete, you can verify them in polynomial time. So this has more relation to NP than NP hard. And NP hard problems are, well, they're hard. As in, for some of them, we don't expect to do some of these problems in polynomial time. So I mean, we want to prove that P is equal to NP. We're not trying to prove that P equals NP hard. I mean, there's even less chance of us doing that, right? So that's why NP hard, well, it's just not that important for us. I mean, if a problem is NP hard and also NP, then that's NP complete, and that's what's important. So if problem is only NP hard but not NP complete, then yeah, they're not that useful. Okay. So that's why I think NP-hard is not that important, but NP-complete is the thing. You can reduce every problem in NP to problems in NP-complete. So if you can just find one problem in NP-complete that can be solved in polynomial time, you have proven that P is equal to NP, because every single problem in NP can be solved in polynomial time. So that is probably the most important statement in the whole lecture, and make sure you really understand it. Every problem in NP can be reduced to maybe just that one problem in NP complete. And actually, every problem in NP complete, by definition, can also be reduced to another problem in NP complete, because they're also in NP. So just one problem here, just one problem in NP complete that you can solve in polynomial time. You can solve everything here in polynomial time. And this is actually what it looked like if P is equal to NP. Makes sense, right? P is equal to NP. Everything in NP complete is inside NP. So NP complete is P. And anything NP complete is contained in NP hard. And NP complete is equal to P. So everything here is also inside NP hard. So that's the picture you have if P is equal to NP. And all right, that's probably the final point I'm making for this lecture. I got a couple more slides, but this is more for completeness sake. If you don't get this, that's fine. So when you think about NP hard, remember how we talked about optimization problems earlier and how they cannot be verified in polynomial time? Well, that makes them NP hard, right? But let's say we don't allow any optimization problems in the definitions. So we only think about decision problems. Are there decision problems which are NP hard but not NP complete? As in, you can't verify them in polynomial time. Well, yeah, but we're not gonna come across them. If you're interested, you can read up on the holding problem. And obviously, you also have problems in there in EXP, but they're not in NP because you can't verify them in polynomial time. So they exist as well, but we're not gonna see them in this course. So we can discuss this more in the workshop if you find this confusing. But really, I just want to say, don't get scared if you see these things, because they are hard and they're beyond the scope of this unit. So if you're interested, then go for it. Go learn more. But I'm not going to test you on these difficult stuff. And also, what are you missing out on? The way I'm doing P for NP is that I remove a lot of mathematics. In particular, we're not doing formal language theory. That is, you probably have seen this in discrete math. You define an alphabet, sigma, and you define a language, L of sigma. Like, let's say the alphabet is just 0 and 1, and then L is a set of bits, like a bunch of bits. And then you define a problem using that language. And then you define complexity based on the, how you can process that language as well. So I decided to skip these because, we don't have that much time anyway, and I think it's way too abstract for you. But that is a big chunk of chapter 34 of CLRS. So if you're interested, go for it, and we can still talk about it if you want. The result is that we're not going to be very rigorous when we are discussing, more complexity later on, and when we discuss reduction as well. We're not going to be as rigorous, but I guess I want to focus on the practical aspect of P versus NP and less on the mathematics, so that's why I decided to do that. But yeah, just saying what you're missing out on. I think most of you will be happy to miss out on that, but yeah. So where are we at? Hopefully at this point, you may have to rewatch the lecture again, but make sure you know what the classes are. Make sure you know what they mean to have P to have NP, NP hard, NP complete. And just remember that NP complete and NP problems, we're just gonna say they're always decision problems from now on. And make sure you understand the difference between the decision problems and optimization problems. And also at this point, you have a basic idea of reduction, or what reduction is. Because that's what we're going to be talking about in the next lecture, reduction. And that is the practical thing that you're going to be doing. You're going to be doing reduction yourself. Okay, so that should be enough for this one. I'll catch you in the next lecture.